Hi, everybody. My name is Vincent Guittot. So I'm working for Linaro, for those who don't know. And I'm working in the scheduler. So today, in this talk, I'd like to discuss about the scheduler interface and how we can evolve. I know that there are a lot of discussion, there are a lot of requests and queries about the scheduler interface evolution, what could be done, what would be the best way. There was some discussion with the nice latency. There are some discussion with QoS interface as a way to provide some hint. But for this talk, I'd like to discuss a bit more specifically about the sched set attribute and how we can use the runtime, deadline, and period to define or to specify the behavior of a task. So I expect some feedback on that. It's more discussion than other things. I have some idea, but I'm interested to know if that makes sense or not at all. So having in mind that the runtime is already used by VDF to set the slice of a task, and the goal is not to replace that, but more to get even more information based on that. So here is a kind of a behavior matrix that. So I have tried to characterize which type of task can use which kind of parameter. The goal is not to define all the runtime, deadline, and period, because most of the tasks probably can't do that. And if they can, that's even better. And based on that, we can characterize the behavior of the task. So I have tried to go around everything. So of course, we have this fully periodic task where you know the runtime, you know the deadline, you know the period, and that's perfect. That would be far easier if that was always the case. I will come back on that, and that's clearly the easiest behavior. So even with a deadline, we can still define some kind of periodic task. Now, if we start to remove one of the parameters, like the period, so yeah, unfortunately, most of the tasks are not periodic. Even if being really strict, not saying that being as strict as the deadline scheduler, where we have a really strict way to behave. Some tasks don't even know. From one run to another one, that can be from 10 milliseconds to 100. It's really more like an event that triggered the wake up and the execution more than everything. But even with that, for some tasks, they have some deadline. We know that the task that wake up because of input event will have to run in a short deadline time in order to meet this overall end user behavior. So that's what I call the sporadic latency sensitive task, where that's happened. We don't know how often, but we know that when the task wake up, we need to react in a defined amount of time. We also have some other tasks where we only know the average runtime. That's a task that wake up from time to time and that will run for an amount of time that can vary. We can see that after that. But yeah, that's probably most of the tasks that we have around. And we have some other tasks where that's even worse, where we can't know the runtime, not at all, or maybe, not at all. But we know the deadline. We know that we have some tasks where we can't run. We don't know how long it will run, but when it's wake up, we'll have a deadline and sometime a period.
And by definition, it cannot run longer than some time to wake up into the...
Exactly. So that's the first input. Yeah, that's what we're. But we don't. Yeah, that can be 1 millisecond with the deadline of 100, or that can be 100 for deadline. That, and probably most of the tasks that we have are in this range where we know that there is a deadline, but from one run to another one, we can go from 1 milli to 10 to 20, whatever. And so when we have a period, that's even better. But sometimes we just have a deadline. In fact, we just know that the task, once it will wake up, we'll have to run before 10 milliseconds or 12. That's it. before I move, I mean, does it make sense, this kind of description? Do you have other things, other behavior that is missing?
I was collecting it. What's the difference between sporadic and random for you?
In the sporadic, you know the runtime, whereas for the random, you don't have any idea of the runtime. You can't say, I mean, even, I'm not asking for really precise runtime, but that give you a kind of bandwidth. So is there anything else? Yeah.
So is this thinking about tasks very individually, or is it taking into account dependencies between them?
No, that's for that. It's for now. That's really per task only. You specify the behavior of one task.
Yeah, this is something that like we care about. Is it's like a series of tasks that need to go off. No individual task has a per defined period. It's just like, you know, when you press the key or when you're doing something, it kicks off a whole bunch of series of tasks, and we're hoping to get it done before, like, you know, 7 milliseconds.
Yeah, that's what I mentioned as the sporadic. You don't have the period. You just know that when the task will wake up and you will have to run for.
So it's usually event driven. So basically, the series that kicks off, an event happens, and here's a series, and then.
Yeah.
Probably what he wants to say is that you do have a deadline, but it doesn't regard a single task. It's
right.
Yes.
The whole chain of the whole DAG. If you have dependencies, you may have a DAG structure.
Yeah.
There is quite a.
So
I studied model, you know, this DAG generic structure with a final deadline, but intermediate tasks just don't have an explicit.
Yeah,
I mean, you can add them a deadline.
Like our deadline is like around usually like 7 milliseconds, because that's about when, I guess, humans notice things. So we care about humans noticing things taking a little longer. Like if you press the key, you want to see it immediately. You don't want to wait like half a second before your text. Like you're typing, and every time you type.
Sometimes when you're below the interactivity range, like below the fraction of a second, you don't really care to have the microseconds or the 10 milliseconds. Maybe it doesn't make really a difference, but it can make a difference from energy perspective. So it's the whole point, I guess, right? Mm-hmm. Instead of going super fast, we can go as fast as needed.
Yeah. Yes, John?
I sort of categorize this as just a throughput-focused task, but often there's throughput-focused tasks that users have initiated or are waiting to finish.
Okay.
And people tend to think that as latency sensitive sometimes because it's like a user perceived latency. But really it's like some amount of random work that has to be done as quickly as possible.
Okay.
And so I don't know exactly where that would fit.
So,
because it's not strict deadline, it's just.
Maybe the compute instance task will be sporadic running, because the runtime and the latency sensitive and those that have deadline.
I don't know the runtime necessarily.
It's just a really long time. As long as.
But I would say that if you know that it's as fast as possible, I mean, and in average 10 milliseconds, and you need a deadline of 10 milliseconds, that's quite easy. I mean, even if at the end you are 11 milliseconds, you will have the same performance level at the end. So, yeah.
I just want to say that the runtime, also with skip runtime, that's just wall clock time, while that may not be
It's
true.
not in fact wall clock.
Yeah.
Why is it?
It's whatever normalized thing we have. I actually posted the patch for the clock infrastructure to expose this time, but then forgot about it. So that's still hasn't happened. We should probably fix that.
But Peter, you mentioned the clock that is used, having a clock which scale with the frequency, but that's not the clock that is then used by EVDF. In EVDF, we will still use the wall clock time, or you want of the scaling clock?
I think we actually use the normal clock.
Yeah, no, the point, and I think that what Christian wanted to raise is that
Yeah, I mean, just the deadline and period might be wall clock and runtime isn't. So, well, they might roughly carry the same unit. They aren't really that complex.
no, here it's all about wall clock time. Now, normally, if I will probably go then, but I mean, if you know that at max compute capacity, you need a runtime of 10 for a deadline of 20, you need half of your max compute capacity. Then if you run at half compute capacity, you will meet your deadline if you're alone. But I agree that from a world clock time point of view, you will run 20 milliseconds, but at half the compute capacity. So that's another level that raised some other problem, I would say, or issue. But yeah, normally that's it's everything's about the world clock time, what you will run at max compute capacity.
So if we look at something like an interrupt thread, that's like a task that responds to a event where it itself is not the deadline or something. It's going to kick off other tasks that may have interrupts. So this is like one of those cases where an event comes in, you want that thing to run immediately, like because you don't know what the deadlines are for other tasks that's going to wake up. And we actually even have server threads that do the same thing. Like an event comes in, they'll demux the events that come out. Where how do you define that? That's where I kind of like I see real time being like I don't see it in the deadline case because when it kicks off, you don't know what the deadline is because it's dependent on what it's going to wake up.
Well, that's the whole DAG stuff. And one of the ways to do this is with deadline servers and give the server a deadline and the server run the individual tasks.
What do you mean by what individual task?
Your DAG.
So if we have like in Chrome, you have a bunch of renderers, you have to go through and tell the deadline server to say, here, run these renderers instead of the main server, like this loopback thing, and try to convince, and this code is written for, every operating system.
Yeah, well, Chrome is big.
Yes.
But we see the same kind of behavior with some microservices which I spoke about in OSPM last week. So you have the main thing, it's like load balance and sort of another microservice, and the whole flow needs to finish within a certain way.
Right.
So that you put inside the deadline server.
Yeah.
For the whole flow you have there.
And then
What's the interface for that?
currently you can't have.
Yeah.
Luca is gonna present essentially it's a C group exception. You have a C group interface.
C groups?
Well, that's one thing.
That's the way data interface too.
I guess we can discuss it.
Sure, it's the same.
I mean, it is task grouping.
Yeah.
Use a C group, do something else, but you need to group the task. So it can be part of both.
So then it's required you to get proxy execution working first before you want to get that.
Probably.
Is there some way to make this generic so that if you're writing an application that's for multiple operating systems that you don't have anything?
We do not control multiple operating systems.
No, that's the point. Is the fact that the applications that people want to run, they be written for multiple applications, just compiled on Linux.
Yeah, well, I mean, they have Linux specific code anyway. And you want uniforms.
Yeah, I mean, and on top of that, all you need to know is if this interface exists.
So yeah, the point there is per task. I agree that we need per group of tasks, but I would say that if we are not even able to define per task attribute, how we can then come to a group of task attribute, which so I think that using C group as a way, not C group with the share and so on, could be a solution, but the goal would be to reuse the same kind of interface also. I mean, we need to compare tasks and then extend that easier than going to the other side, in my opinion. But
yeah, I just wanted to point out that I mean, you can have tasks that are like one or more, like more of these as well, right? And then they could be switching between behaviors, like
you can. I mean, so
like something that might be fully periodic now is sporadic, and then it goes
you just have to change your. I mean, you have an attribute to say to set that. That's the point.
Yeah.
I mean.
Yeah, but if you keep changing attributes, that's like overhead, right? And then.
But yeah, but I mean, probably we'll have to check. But in any way, if you want to give an int, that will be an overhead. And if you want to give an int every millisecond, yes, there will be an overhead. We can't do anything about that. I mean, whatever the interface, even if it's any other things like a simple.
Yeah, but and it's also like it's sometimes not up to the task. It might make a syscall that blocks on a lock, right? And then now it's like now its behavior changes because the lock introduces a sleep pattern because of the contention and whatnot. And it's not up to the application to.
But that's not true, right? Your workload defines what sort of a behavior you're looking for, not what behavior you're actually getting. And I think what you want to try to provide is the behavior you ideally want, as opposed to what you get, and then hopefully the schedule will help you get that behavior.
So it's only int. I mean, at the end, the goal. I mean, it's not like deadline scheduler where if you provide wrong int, you will be throttled or you will be dequeued. There, just to say, okay, that's what I want. And so I would say sometimes maybe quite often you will not be able to get that, but at least we know. Naturally that. I mean,
the other thing is like if you want to ask for runtime, you don't know what CPU architecture you're running at, so it has to be some scale invariant.
So that's why. So Peter has this patch where you have this timer clock interface, this new clock which scale with the frequency. So you can know what would have been your execution time at max compute capacity.
Okay, that's cool.
If only Morten didn't present the thing that. But yes.
So that's another thing that few things that we can do with this runtime deadline and period beside this slice. But we can define some peak bandwidth for a task, which is often something we are missing. We have some small tasks that we'd like to run as fast as possible, for example. But that's not something that, it's not the utilization that will stay quite long on the run queue. We have the average bandwidth, where, it's more stable, and the lower the mean bandwidth that we can introduce. So all this computation are not that far to what is done in the deadline, where they're computing a minimum bandwidth for the CPU. It's just that just some int for us. And even if you only have the runtime, if you know in average how long you will run, you can already estimate what should be your utilization. So I mentioned a lookup table to provide an estimation of your utilization. But you can always provide that. Right now, we are estimating our max utilization at runtime, at the queue. But I would say if the task already know is runtime, we should better use that instead.
So, just for the theory folks, Tomas will probably correct me, but what I remember when we were studying about deadlines and periods, where more often than not, deadline is equal to period.
You can use deadline equals to period, or you can use deadline lower than period.
But practically.
No, you mean for the deadline scheduler?
But even practically, what's the difference between
I think, for example, what Steven was saying, let's say that you have a periodic queue that is periodic, so there is a period, but when that thing fires, you actually have a shorter deadline to service it. Yeah. So that is also maybe useful to model that thing.
Yeah, typically you have a task that wakes up every 10 milliseconds that it need to run 1 millisecond, but to finish in 2 milliseconds. Your peak bandwidth it's half the compute capacity, 50%. But the average, it's only 10% of the CPU as a whole. So you know that in average, you will use 10% of your CPU, but with a peak of 50%.
Do we allow overcommit?
No.
I think that's also an issue. There's going to be cases where, I think I mentioned this 2 years ago, where, things will want, they could, schedule it as, if things get overcommit, we just want degradation of the system, not, you can't do this anymore. You can say, these are the lines, but it happen that these wake up at the same time. Yes, there's going to be, one of them's going to miss their deadline. But this isn't a real-time application. These are normal applications like doing, playing video games, whatnot. If you miss your deadline, someone might get upset and get shot in whatever video game they're playing.
And this is why I've been telling people to implement a fallback to fair instead of the hard bandwidth constraint becomes
Let me, so you run, but you just fall into fair and miss your deadline.
Yeah.
Yeah, that's
currently we still.
Exhaust your bandwidth.
Yeah, so currently when bandwidth is exhausted, we just fully throttle it. But the alternative is to just drop it in fair.
Yeah.
And the initial deadline patches had this. And then we stripped it out because simpler patches is more better. But if people want this, and it seems they do, I've been telling people for years to just add this. It's not hard.
And then will they get promoted back to deadline?
When we're done.
So that you will then move it to the different schedule. How expensive is that?
Better than throttling.
Okay.
But for that, you need a period, which is not what we have most of the time. So yeah, and in the test that I'm running locally, in this case, I'm overriding the util_est instead of creating yet a new util guest or util user, and then we'll have to combine the estimation. In this case, I'm just overriding the util_est because the util_est is just at the end what we are trying. We try to estimate the utilization. If we have all the value, why we just keep that? So, and in this case, yeah, we don't need to estimate the task utilization because we have this estimation, and then we have the util average that behave as usual beside that. That's really two things. And the last line, but I haven't gone there, is that if we have this information, this can be used outside the scheduler. Like if we have a bandwidth, we all know it's sometimes quite difficult to scale, interconnect, cache, memory bandwidth, or storage bandwidth, or whatever. So
that depends on the workload then. So
yeah,
it's not just a runtime.
No, I agree. But yeah, that's my point is that this value, the goal is not to say that's a scheduler value only for scheduler, but we have a bandwidth. Now I agree that what does it mean from a pure, if we're able to characterize the type of task, then we can probably see if it's a memory bounded or CPU intensive. But yeah, that's an information that we not always have only with util average, because with the util average, we don't have this kind of, we know the utilization, but not, we don't know really how it's move around during the time, during the period. So that gives us more information.
So one of the things that we mentioned last year was to add system calls or other markers that a process can place for us to derive an average period and an average.
Yeah, and the yield thing. Yeah.
Like start marker, if I'm starting a new job, to differentiate between waiting for a new word, which is a very common thing, and being blocked on random resource.
Yeah.
Because currently, from a scheduler point of view, both is blocked. We can't tell one from the other. If we were able to, we can infer more information about your workload.
Probably.
Guesstimate some of these numbers.
Yeah.
But that's equivalent to having like a syscall to clear utilization more or less, isn't it?
I'm not sure if it's equivalent to saying clear utilization, but it's a definite marker of state. Yeah.
Even something to say I'm waking up this other thing was one part of the graph. Right?
So yeah, for the DAG thing, the DAGs are a pain in the ass because there's inherent concurrency. Yeah. Just, the trivial case is a linear one.
Yeah.
And that can be expressed. I mean, we can create an interface. Either cbooks or PRCTL or hack something horrible. See if it works. But the concurrency in that is always painful, at least. And then there is the problem that a lot of tasks or programs will wait a task in a particular class. Like it will pass the work to a work queue, which is a multiple of threads waiting for work. So then that would need, you would need to be able to express this class of tasks instead of just this one. And then say one of these, not multiple. And so while the theory of that is very appealing, the actual details of trying to get something useful out of it needs a lot of details sorted. But if we can pull it off and get something that is actually useful, it will be a very powerful construct.
Okay. Minutes?
It's more 15 because it's left.
Okay. Over there. So yeah. So then I was going. So the latency sensitive task, which is probably the most interesting and not the periodic one, it's probably the one where we lack to clearly estimate that. So the runtime deadline and replacing that the UTLS just enable us to reach directly the right OPP. And even if at some point your runtime is effectively lower than what you set, you will keep, you're sure that your UTLS will not decrease or bump up. You will ensure a minimum bandwidth for your task. And you can easily use that then in the EES and task placement, so you can ensure if you have enough compute capacity. And also, I haven't put that there. Yeah. You can have an idea if the sum of the utilization will be higher than the compute capacity. No, that's probably for another one. But the runtime, because it's also the slice, you can also use that to know where on which CPU to place. You can then select. That will be for the other talk about how to use more int in the energy aware scheduler to select the CPU where you will try to run first. But if you have a runtime right now, you have a slice. The goal is normally you should be able to preempt at wake up another task with a longer slice. So the shorter slice should run first at wake up. So you can select a CPU where you will run first, and you can try to prevent all the smallest slice being packed on the same CPU, because otherwise you are increasing your scheduling delay. That's not. There is other corner cases that need to be managed, but yeah. At least you will ensure that with the peak bandwidth that your task will meet or not their deadline, and you can sum up. Similarly to what is done with the deadline, a bit lighter, but and the other thing is that yes, right now with the EES, because I'm mainly focusing on EES, it's energy first, but we can imagine that in some point that worth selecting a CPU which is maybe a bit more power hungry, but at least you will meet the deadline. That's another thing that we might need to consider in the EAS, is that maybe sometime it's worth to waste some power or some energy just to meet the deadline. And with the push task that I have sent, you can even still consider enqueuing a task on a CPU and then expecting that some of the tasks will be pushed without waiting them to sleep and wake up. You can anticipate. You have a more interactive or task placement that we have right now, where right now we are just waiting for the wake up to ensure that everything is going well, which is fine, but not enough.
So the other latency sensitive case, when as an oracle we had come up with, was from slightly different direction. That was more that we know we don't run for a very long time, but we want to run quickly, and it was more expensive for us to find a CPU to run on.
Okay.
than it was to actually run on any random CPU.
Okay. But yeah, so there at least you can find a CPU where you're sure to run first.
Yeah. But as long as you're running the shortest runtime first.
Yeah.
Right. But you want to pick a CPU quickly,
Yeah.
as opposed to pick a CPU that you have shortest.
Okay.
We have
Yeah, okay. Yeah.
That's like
Yeah, I see your point. But yeah, so yeah, I have mainly focused on the ES and the way that we need some interaction. So yeah, the fully periodic task is just the easiest one, probably not the one that we can see most of the time, even if I'm pretty sure that we have some of them. We have a number of tasks where we know in average how long or what will be the max running time. So you can estimate what will be its utilization. Even that the point is that there the goal, it's not, you don't have to be accurate about your runtime because it's not a hard deadline scheduling process. But if you know that your max running time is this value, you can use that to just set the slice first, that give an idea, and also set its util estimation without waiting for any DQ or without all the things that we are doing right now to try to keep the right util estimate all over the use case that we can face.
So will this be the replacement for base slice for each task? Is that what you're?
So there is two things. One, it's about setting its util estimation. So how long you will, how much compute capacity you need or you expect. And then, yes, that can be used then to place in the scheduling. I mean, if you have a long run slice duration, you can probably go wherever you want. If you have a short one, then you will probably look for the right CPU. And yeah, that the estimation of the utilization will be better than, I mean, because you're sporadic, you don't know. I mean, you can't really estimate based on the NQ and the DQ, because you can have 1 second sleep time or 10 milliseconds sleep time. So you can't make any assumption on that. That's another thing where I think that can help us in the estimation of the utilization of a CPU.
Sorry, I didn't get what you are looking at then. What you are looking at.
So there, if you have just a task to say, okay, when I'm waking up, usually I'm running 100 milliseconds.
Yeah.
Based on that, I can estimate what will be its utilization from a PEL point of view. So you can say, okay, by default, I
mean, you should rely on how often you are waking up in the end, no?
But that's a point. But yeah, in this case, because your period can change from one run to another one, you can just say, okay, if a task is running 100 milliseconds, the PEL estimation can be that, without taking into account the fact that you might have sleep only 1 millisecond or 100 or 1 second. That's the point. You can estimate that. That's a first guess about your utilization of the CPU.
And the runtime, you anyway have only the historical information. You know how long it's been running in the recent activations.
Yeah. Yes.
But from a quality of service perspective, we are talking about different things. If you derive like stuff like UTLS, for instance, based on information the user gives you, I mean, there's a lot of control you lose, right? Like, it's a different thing to say we install more markers to know when an activity starts, and then we do the calculation in the kernel.
Yeah.
If we rely on user information, like quality of service is like very quickly abused, for instance, or something goes wrong, and then it's who's actually.
So yes, I agree that they can abuse, but I mean, in this case, we should not look for a user space interface because they can always abuse of. I mean, we can always provide some maximum or minimum value. So at some point, we need to balance between either we expect the user to provide you some hint of the task, and we have to trust it up to a level.
To trust it, you can just measure it and see, the user was wrong, so we can just
I agree on that.
That's why it's a hidden.
We can always mitigate what he's saying and providing a max value because we know it's insane or things like that.
Like just providing interfaces where you stay, like an activity period starts or what before. It's a different kind of quality of service because you have it still under control what you do with this information. If you just believe the user, I want to have this utilization or bandwidth, then
So the user input is just what the user thinks, and not, and they may be way off. Like, it may be based on running on a different system, for example, or similar.
Yeah. So that's why it's the point there. It's run time. So then the goal of the scheduler is to translate that in some scheduler int like utilization. But we don't have any strong rules to have a 1-1 map about. So it's up to us to decide what makes sense. I think that setting the utilize based on that makes sense. Now we probably want to cap the max utilization if we think that the user will just abuse that. Then there are this random latency sensitive where we don't have any runtime, we only have a deadline, and that's probably the most, yes?
I have a question. If a task is running for some time, or if a task is waking up every X milliseconds, it's something that we could also measure. So instead of relying on the user information, can't we just measure this and make decisions based on this average runtime that people are?
Yeah, that all the point is that some tasks, for example, this sporadic runtime, the goal is that the average runtime is meaningless in the sense that it can be 1 millisecond to 100 from one run to another run. And how do you,
for some time, for some tasks, this average runtime is going to not be, it's not going to be stable. But for periodic tasks, you can more or less, there should be a way to detect that this average runtime is stable and to say that to detect that the task is actually periodic. Yes.
But that's almost what we already have with the average, the util average and the util-est. If you have a fully periodic task, right now the util-est is quite good to estimate its utilization. But the fact is that we don't have that much such periodic task running on. From a runtime and period point of view,
But the utilization?
Yeah.
A task can run 1 millisecond, sleep 1 millisecond.
Yeah.
And do this periodically, you will get a utilization of 500. Or a task can run 10 milliseconds, stop during 20 milliseconds, and will also have a utilization of 500. So in the util average signal, you don't have the information of how much on average the execution time is, but you could. It should be possible to measure this.
Sorry, I'm not sure what you mean.
I mean that you can have two tasks which they are going to have the same util average, but they are not going to have the same execution time every time.
Okay. Yeah.
And it should be possible to measure this and put this inside. But how do you decide if it's reliable or not? If it's not just, how do you decide that? Even if we are measuring the runtime, we can do that. But how do you decide that it's a real periodic task so you can set a period, a runtime, and maybe a deadline? Or if it's just a temporary behavior, and then you will change
And you will have to, how do you detect that finally you're wrong?
So right now, in that, the signal is also not, it's a hint, you don't know what's going to happen. In the same way, you can say that this time has been executing each milliseconds for the past 2 seconds. It's really likely that the task is going to run this milliseconds again. So it's not, you don't actually know what's going to happen, you still have a good hint, except for sporadic tasks.
Yeah. So we can add yet another metric, but yeah, that that's mean another thing that need to monitor, and we need to check how it scale. That the point that the goal there is not to add another metric, because we know that the metric is not always true, but to say, okay, if the task know what it wants, just let him specify that. But yeah, we can, but we have to look at the scalability. One advantage of the pelt right now is that the execution is the same, whatever the number of tasks, whatever the number of scheduling, and switch at the point. That's one of the reasons we are using that. The more complex case is that when the task set a deadline but don't set any runtime, and we don't know what to do with that. Right now, the simple things that we can do is, if the deadline is shorter than, you can set a slice based on a maximum slice based on the deadline, because you can expect that if a task set a deadline of 2 milliseconds, its slice should not be 3 milliseconds. And you can probably also set a minimum UTLS, but there it's more complex because you can't predict any kind of sane value. You can predict a value, but I'm sure that someone else wants another value because of ABC. So, but at least we can set the slice. We can use that to update the slice, the minimum slice or the maximum slice in this case. The two open issue may be, the one is that right now the sum of UTLS, that's something we have discussed, but the sum of UTLS is always far higher than the util average, because we are summing the max value of each task, and each task can't be at the max value at the same time, because only one is running at one time, so the other one is decaying. The only advantage with the runtime and deadline is that we should remove part of this if we set the UTLS of a task with the bandwidth. We should not face this sum of UTLS larger than the real utilization of the CPU, and switching to the overutilized mode and so on. And the other thing is that the goal is that we should probably not use the UTLS for overutilized, but only for the OPP selection, just to set the bandwidth, but not to say if a CPU is overutilized or not. I don't know. No, so you can still use util average. That's one thing. I'm just speaking about the UTLS. The UTLS is the estimate of each task, and right now the UTLS is clearly overestimating the max compute capacity of a CPU.
But the util average is inherently capped, so you couldn't really.
No, it's not.
Well, to some extent anyway. Using it for overutilized, using just util average will work, right?
For the overutilized, I'm not sure. That's another thing. I'm not sure. What is clear is that the UTLS, if you use the UTLS, you will be overutilized even if you have some idle time on the CPU right now. We discussed, it was with you, Dietmar or Pierre, about this two tasks running 40 milliseconds every 100. The UTLS, the sum of UTLS is higher, whereas we still have some idle time. But that's the sum of UTLS, which is wrong, because we are taking the maximum utilization of both tasks, but they never at the maximum utilization at the same time. That's not possible. That's just what they would like. But so with this, maybe that should be better.
You do want to provide some room for them to grow into in case they do.
Yeah, no, I agree. No, that's one thing is that, if we start, some of ETLS is one problem for us with ES in the sense that we trigger the overutilized test really often.
I think we should take this offline because we got other time. Right. Thank you. Thank you, Vincent.